video is going to be on the concepts of types 1 and 2 errors and power. So I'm hoping this little demonstration helps clear up what those are saying. So here's our setup. We're going to be learning about, or we're going to be investigating the proportion of orange candies in this machine that contains Reese's Pieces. So some people like to think I don't say that right. In my opinion, I do. Reese's Pieces. This is on rossmanchance.com. It's a statistical applet website. It's got a lot of great things on there. So we're going to use this to investigate these concepts. So here's what we're going to do. We got to make a hypothesis, right? So this is our population. This whole machine contains all of these candies. The candies are our population. We're interested in their colors, and what we're actually interested in is the proportion of candies in this machine that are orange. So we're trying to make an inference about this population, and that inference is learning about this true proportion of orange. So we take a guess, and we're going to test different values for our hypotheses. So one value that we might test might be 50%. We might want to know, like, maybe we think that there's 50% orange in there, and then our alternative might be that the proportion of orange is greater than 50%. So these are two viable hypotheses we can test, and we could test them at the significance level of 0.05. So what we're going to do is we are going to take random samples from this machine, and we are going to run our hypothesis test for this type of. We're not going to check conditions. I'm going to go ahead and assume that they are all met and things like that. But we should be able to pick out what type of test we will use. And for a scenario like this, we're talking about a proportion. So we're using a z-test of some sort. We're talking about a one sample, one population. So we're going to use this. We're going to use a one proportion or one sample z-test about a proportion. So that's what we're going to use. We are going to do this on our calculator to help us make decisions. So we're going to take a sample from this population, and we are going to see what is the sample proportion. So we're going to take a random sample of 30 candies and determine the sample proportion of orange. Record that, find our p-value, make a decision about the null hypothesis. So this is our null hypothesis. We have our hypotheses established to help with our conclusions. And so over here, this machine, this applet, gives me the option to set what I want this population of candies to have regarding the proportion of orange. So I am going to set the probability of orange for this machine to be 0.5, which is exactly the value we are hypothesizing. Okay, so this isn't important here. So what I'm setting this at is a 50% orange. That is going to match, or that does match, exactly what our null hypothesis is. So if we were just guessing, we would have been a great guesser. We would have guessed correctly. So let's just see what happens as we take samples of 30 candies from this population and run some of these hypothesis tests using the z-test. Okay, so it's going to take a few minutes, but I hope that this draws out some of the things some of the concepts and core ideas related to type 1, type 2 error and power. So let's see. So we got this set up. There's 50% orange in here. Let's take a sample of 30. So before you go, you should say to yourself, oh, I should expect about 15 oranges, right? You take a sample of 30. Half of them should be orange. Let's see what happens. So take one sample. What is that? 14. Okay, so it's pretty consistent with our expectation. So nothing too surprising, but our p-hat, so over here, our p-hat would be 14 out of 30. Okay, so this is our sample. First sample, we had p-hat 14 out of 30, number of oranges. Let's get our p-value and make our decision. So we're going to go to our calculator and do a one proportion z-test. Our null hypothesis is that this proportion is 0.5. We just got 14 out of 30. Our p-value is based on the direction of our alternative, so we're doing a greater than. And we're going to go ahead and calculate this. For this, I'm just going to calculate it. Okay, p-value, what do we got? So p-hat, they converted the 14 out of 30 to its proportion. The p-value is 0.642. So what conclusion do we make? So 0.642. This is also serve as good good practice making conclusions about hypothesis tests. So since our p-value of 0.642 is greater than our significance level of 0.05, we fail to reject the null hypothesis. To reject the null hypothesis. In other words, we believe it is possible that this machine truly has 50% orange, which we hope it does, right? Because that's what we said of that. So this conclusion is consistent with what our machine is set at, and it does not reject this idea. It supports the null hypothesis. It does not support the alternative. So we fail to reject the null hypothesis. That's our conclusion. So let's do another sample here. Let's see what happens. So we take another sample. This time, we got another 14, so we're going to have the exact same conclusion. So I'm going to go ahead and run through a few of these here. 4 out of 13. This is ditto and ditto, same thing, fail to reject. Let's do another one. Okay, this one was sample number 3. This is 11 out of 30. So let's make our conclusion for this sample. So we go back in here. If we run this test again, so we're going to pick number 5. So if you're doing this, do this with me. It's good practice. Go to 11. Everything else is good for us here. This time the p-value is 0.93, so definitely larger than, so we still have a fail. I'm going to write it like this for a second. You cannot write it like this, so I'm just doing this for to speed up the process. Fail to reject the null hypothesis. This is just the carried down p-value from the one above it because it's the same data. Okay, so far we failed to reject. Draw another sample. Okay, this one was a sample of 15. So we come in here, we got 15 out of 30 this time. Go back, you run this test. Oop, it's 15. Oop. Okay, p-value should be exactly 50% because isn't 15 what we expect? It would fall smack dab in the center of our distribution. So this is p-value is 0.5 or 0.5. So again, since 0.5 is larger than our significance level, we fail to reject the null hypothesis. So I'm going to do just a couple more here. Okay, this time I got 12, so sample number 5 resulted in 12 out of 30. Okay, so let's just like logically think through these to speed this up a little bit. 12 out of 30 is below 15. We would calculate, our p-values are all being calculated using an approximate normal distribution, shading to the right side. So 15 should be in our center, right? So that should be 50% there. This 12 is a little bit below that. So our p-value should be greater than 50%. So definitely not less than 0.05. We failed to reject. So this whole time, if we're searching, we've been failed to reject, failed to reject, failed to reject. If we are going to reject something, then this p-value is going to have to come out to be less than 0.05. So let's just, see if something like that could happen. So we got 17. So let's take a look at this. So let's take a look at 17 here. So sample number 6 is 17 out of 30. So let's get our p-value for that. And stat test 5. Calculate your p-value. Okay, that one was 0.233. So that p-value. So it's not quite small enough to reject anything. It's still this p-value, since the p-value 0.233 is larger than 0.05, we fail to reject. In other words, we still support the 0.05 or the 0.5 50% orange hypothesis. So fail to reject. So you can see like kind of what we're doing here. is we're just going to keep generating samples like this. So this time I'm going to generate 10 samples and look at some of their p-value or some of the sample proportions we get from that and see what some of the conclusions we can make might be. So I take that and I generate 10 more. Okay, so in this, or actually this is our most recent sample gave us 20 oranges. So that would be sample number 10. So let's say, we keep going. You can see what those values are down here. We got 1 at 20. We got one over here at it looks like 11. We had a couple more at 14, around 15. But sample number 10 told us that we got 20 out of 30 from this population. So let's get our p-value. So we go to our calculator, stat, test, and we pick number 5. Got 20 here, 20 out of 30. Calculate our p-value. Okay, this time the p-value, so we got our p-hat is 0.667, which makes sense because it's 2/3. We got 2/3 orange. The p-value this time is 0.034. So we got 0.034. Okay, this thing is less than 0.05. So what conclusion should you make? Based on the sample, our conclusion would be that we reject the null hypothesis that P equals 0.5, P with orange, P orange, in favor of this proportion of orange being greater than 50%. And that should make sense, right? I mean, this P hat right here that we got is 67% or 2/3. I mean, that's definitely not 50%. So here's what happens. We make a mistake. Didn't I set this up? I set this population of Reese's Pieces, right, to be exactly 50%. I set it right here. This machine is full of exactly half orange Reese's Pieces. When we took samples from that population, most of the time we did not reject this idea as we should. We should not be rejecting this very often because that is truly what is in this container, exactly 50%. We would have guessed correctly. But because of sampling variability, because every time you take a sample, you are not guaranteed, you're going to get different values of p hat. There is a chance that you reject the null hypothesis even if you guessed correctly. So in other words, we would reject this idea although it is true, and that is called type 1 error. So this is called a type 1 error. because we would reject the 50% claim about the Reese's Pieces of the true proportion of orange being 50% or 0.5. We would reject that even though it is true. Well, that's kind of bad luck. So this is the definition of type 1 error, is rejecting the null hypothesis if it is actually true. That is the definition of type 1 error. And that's what we would have made. And we have to be okay with that. There is a chance. This thing right here, this decision was not made because we had bad methods or conditions didn't check out. This was made by random chance. And that is what type 1 error is. By some random chance, we made the wrong conclusion. In statistics, we can never be 100% certain. And the sampling variability and that with all the different values of p hat we could get when we do this, when we sample from this population, reminds us that unfortunately sometimes we take a sample and maybe it doesn't represent the population as well. Even though it was randomly done and everything was done well, our methods were followed carefully, we may make a wrong conclusion, and that's part of statistics, and it's part of data analysis, and you hope that doesn't happen. You try to minimize that, but that does happen occasionally. So this is our example of type 2 or type 1 error, sorry. Okay, so now we're going to go ahead and go into type 2 error. So you might have to split this video into two. I'm leaving this up to you. You want to check it out and watch a little bit, but this is, I think, a good example of what type 1 error is. Now, type 2 error, we're going to do something pretty similar, okay? We're going to go ahead and run the same sort of idea, okay? We're going to leave so we're going to look at type 2 error now. We're still going to look at our proportion of orange. We're still going to have the hypothesis that is 0.5, okay? And from here on out, I'm just going to write P for proportion orange. Our alternative, let's just keep it where it's at. We're still going to have our significance. I mean, we're going to do the same thing here. There's going to be one small change to this, though. So we're going to have that. We are still going to run a one sample z-test for a proportion. So we're still going to do one sample z-test for a proportion. Okay, and we're going to record similar data. So okay, so we're going to have our data table, same sort of idea. Okay, that's enough. So we have our sample number. We're going to have our p hat from our sample. We're going to have our p value, and we're going to make our null hypothesis decision. Okay, we're going to make our null hypothesis decision. So let's try this out. Okay, but here's kind of like the catch-22 at this one. So the last time for type 1 error, I set the population to where it was actually matching what our hypothesis was. In other words, we would have been a really good guesser. We would have said, we did a great job today. Although we learned there's a chance we make an error in our conclusion and we reject our guess, but generally we didn't reject very often. So now we're going to have the same sort of hypothesis about this population. We're going to guess that there's 50% in here. However, I'm going to make the reality that this proportion is 60%. Okay, so I'm going to make this population 60% orange, and we're going to do the exact same thing. We're going to take random samples of 30 pieces and calculate p hat, find the p value, and make a decision about this claim we made. So let's try it. Let's do 10 samples. I'm going to reset and redo for a second. Let's just do 1 to start. So draw a sample. 1 sample. Okay, first number of orange candies that we got was 21 out of 30. 21 out of 30. So we get our p-value. Run our test here. We're going to do this just a couple times, not 5 or 6 like last time, but we're going to do this a couple times just to make sure we understand. Okay, our null hypothesis is 0.5. We got 21 out of 30. Calculate. P-value 0.01. Okay, 0.01. What's our decision? Our p-value is less than 0.05. This means that we reject the null hypothesis. In other words, we don't believe that the true proportion of orange is actually 50%. In fact, this p hat, if you go ahead and calculate the decimal, what do we see it is? It's 0.7, right? It's 70%. So this sample had 70% orange in it. Now that like maybe shouldn't shock us, because what population are you pulling this from? You're pulling it from a population that is 60% orange. So I mean, it's definitely possible that you get a sample of 70% orange. So let's do another one here. We draw another sample, 21. Okay, so we have the same conclusion. So it happens to be back-to-back 2 samples in a row. We got 21 out of 30. So our p-value is going to be 0.01 again. And we're going to make the same conclusion. And again, remember our alternative. Every time we calculate a proportion, it lives on this p-hat line somewhere, this approximately normal distribution. And we are always calculating our p-values with area to the right, because we're working with a one direction or one tail hypothesis test for greater than for the alternative. So that's what we're checking. Okay, so that's sample 2. Let's do a couple more here. Next sample, 15. Okay, so let's see what we got. Sample 3 is 15 out of 30. So let's calculate this p-value. This p-value is no longer, well, let's calculate the p-value, see what happens here. So we have a new conclusion that could happen, or a new p-value. So I'm just backing up. Let's just calculate this. So we had 15 out of 30 in this most recent sample. We expect 18, so it might not be that close. 60% of 30 is 18, so 15%. So we'll see how we do. So let's get this p-value, and go to stat, test, and we go to 5. That should say 15. Calculate. P-value, 0.5, or exactly 0.5. So our p-hat sample proportion is 1/2, because we had half of the orange, or half of that pieces be orange. And then we had a p-value of 0.5 because according to our null hypothesis, what should you expect to occur? You should expect 15 based on our null hypothesis. So this p-value is 50%. So what's your decision? 0.5 is bigger than 0.05. This is fail to reject the null hypothesis. In other words, we support that the true proportion of orange is 0.5. Let's star that for a second. Let's see, let's do 4. Let's do another sample here. Okay, this one was 21. 21 out of 30. We have the exact same conclusion as before. 0.01 is you reject the 50% claim. About 21 again, so we'd have the same conclusion. So if you notice what we're doing is we're rejecting pretty often, right? We're doing that. So this, like here, this is sample. We had 5 was the same as the ditto number 1, and the one above it, same thing, same thing. Sample number 6 we took had 19 out of 30. Let's see what that conclusion is. So you go here, you go to run your test. And this was 19 out of 30. Its p-value was 0.07. So this is 0.07. Okay, so what does that mean? Based on our significance level, 0.07 is larger than alpha, 0.05. So this is also, we fail to reject the null hypothesis. In other words, you support the 50% the 50% claim that half of this population of pieces is orange in color. So I'm going to star that one too right now. So if you notice, so far we've rejected at a pretty high rate, right? We've rejected this idea that the proportion of orange in this machine is 0.5. And we should, because what is the actual proportion of orange? It's 60%. So like our hypothesis is incorrect. Like it is not true. So it makes sense, and this proportion is larger than 50%. It makes sense that we are rejecting this number of 0.5 pretty often. However, there have been 2 times where we would not have rejected the 50% claim, even though it is clearly wrong. I mean, that population is set for 60% orange Reese's Pieces. So this thing right here would have had two errors made by us. These are called type 2 errors. And that's when we fail to reject, this is the definition, is you fail to reject the null hypothesis if it is actually false. If it is actually false. So this thing right here, we made that error 2 times. Even though our population is definitely not 50%, we got sample data that was too close to 50% for us to throw out the 0.5 claim. So we would have made an error, a wrong conclusion about this box or this machine of Reese's Pieces. So in this case here, we would have still supported the 50% claim, and we wouldn't have really supported this, that this proportion was any bigger than 50%. We had no reason to believe it's not 50%. So we would have made these two conclusions. So this is called a type 2 error. It's where you fail to reject the null hypothesis if it is actually false. So the last thing that goes into this is, someone did ask, like, is power tied to type 2 error? Absolutely. You would like the probability of type 2 error, the probability of these mistakes right here, to be as small as possible, right? Like if this population is truly not 50%, which it isn't, then we would want to reject this 50% claim as often as we could with a high probability. I mean, it would make sense, right? So power is defined to be the probability of rejecting the null hypothesis if the null hypothesis is actually false. Okay, so let's take a look. Let's take a look up here. Based on our data, we only did this 6 times. Now imagine if you did this 600 times, okay, and you started to generate a simulation of 600 different sample proportions and 600 different conclusions. And what are you doing? Based on our data here, according to what we see, what is the probability of us making a type 2 error? Well, we did this 6 times, right? We made a type 2 error here, and we made a type 2 error here. So the probability of making a type 2 error for this test is 2 out of 6. What is the power of this test? The power is the probability that you reject the null hypothesis if, some people use the given bar, the conditional probability, if the null hypothesis is false. Well, in our context, right, in this machine, isn't our null hypothesis false? It should be. We guessed 0.5 and our actual population is 0.6, a 0.6 proportion of orange. So this thing right here, what's the probability that we rejected when we should have? And that answer is 1, 2, 3, 4, 4 out of 6. So these two events, I mean, either only one of these two things can happen, right? Where we reject the null hypothesis if it's actually false, fail to reject if it's actually false. They're complementary. They do add up to 1. So some people, so we should at least understand that the probability of type 2 error is equal to 1 minus the power, and vice versa. So the power is equal to 1 minus the probability of type 2 error. So the last thing is uh, why is this called power? Okay, I want you to think of it like this. Why is this term called power? This is the probability of rejecting a null hypothesis if it is actually false. Power means strong. It's a strong test. So we have tests that are more powerful than others. And more powerful tests reject a wrong null hypothesis with a higher probability. I will give you a quick example. This test that we did over here, if I change 0.6 to 0.7, now the true proportion of orange is now even bigger compared to 0.5 than it was. Look at what happens here. I'm just going to draw some samples for a second. We'll do 100 of them. So if you take a look at our table over here, what sample proportions caused us to make a wrong conclusion, to fail to reject? Like 15. Did we get any that were? We got 5 out of these 100 that were at 15. So for every one of those 5, we would have said we failed to reject a 50% claim, because if you think about it, out of 30, 15 out of 30 is exactly 50%. However, if we start to get to like 20 or more, or 21 or more, where we are rejecting this hypothesis of 0.5, we see that there are a lot of samples here where we would have rejected this hypothesis of 0.5. I mean, if you just pick one of these 21s, it would have made this conclusion right here. If you would have picked this 19, okay, 19 would have made this conclusion right here. So only this little section right here would have resulted in wrong conclusions. This whole piece over here would have resulted in correct conclusions. So if I just do a little probability, let's see, that's 20. This thing right here, all of these little samples, these that we found right here, the 69 of them would have led to a correct conclusion. This is a 69% probability. This test has approximately 69% power, because these little samples, if we got 24 out of 30, you're certainly going to reject a 50% hypothesis, aren't you? I mean, 24 out of 30 is 80%. That's pretty high. So this is the idea of power in type 2 error. And for us, we just need to understand what these errors are and what they mean, and how to interpret them. You don't have to worry too much about the probabilities related to that, but it is very important to know and understand intuitively. So I think the last thing we are going to do is just kind of talk about what these errors look like and what the consequences of them are. So this is an old AP free response question from 2012, and this is discussing the different hypotheses and what type 2 error is, and then what we should conclude. So let's take a look at this for a second, and then we'll be, I think, probably pretty good to go for right now. So my hope is this little exercise, this activity I showed you, at least hammers home the idea of what type 1 and 2 errors are in power. So a recent report stated that less than 35% of adults in a certain city will be able to pass a physical fitness test. Consequently, the city's recreation department is trying to convince the city council to fund more physical fitness programs. The council is facing budget constraints and is skeptical of the report. The council will fund more physical fitness programs only if the recreation department can provide convincing evidence that the report is true. So someone has a report, they're making a claim, they are going to test this hypothesis. So the recreation department plans to collect data from a sample of 185 adult residents in the city. A test of significance will be conducted at a significance level of 0.05 for the following hypotheses. P equals 0.35 and P is less than 0.35, because that is what they are trying to figure out about this proportion, and P is the proportion of adult residents in the city who are able to pass the physical fitness test. So this would be a hypothesis test set up for you, just as a comprehension check. You should know that this is a one sample z-test for a proportion. If you're using your calculator, it would say one prop, which is acceptable to show understanding. One prop z-test. Okay, either one of those, but you should recognize that as one prop z-test. Describe what a type 2 error would be in context of the study, and also describe a consequence of making this type 2 error. So what is type 2 error? Type 2 error, according to what we learned, would be to fail to reject the null hypothesis if it is actually false. So what does that mean in this case? Type 2 error would be we fail to reject the null hypothesis that the proportion, what are we looking at? Proportion of adult residents in the city who could pass the physical fitness test. The proportion of, you need this for context, adult residents in the city that pass or could pass the physical fitness test is P equal to 0.35. In other words, we support the 0.35 claim, right? Okay, so this is the first part of this. Type 2 error is you fail to reject the null hypothesis, which is the proportion of adult residents in the city that pass the physical fitness test is equal to 0.35. In other words, you support it. Although the null hypothesis is actually false. And what does that mean? False would mean that the proportion of adults that would pass the physical fitness test is actually less than 0.35. Like, that's the true reality. So let's say you go out, you take a sample, you do everything okay, it's randomly done, all the conditions are met, you feel pretty good, you come back, and you end up failing to reject or supporting this 0.35 claim. However, by some random chance, the true reality, unbeknownst to you, that you're not aware of this, is actually that this proportion is less than 0.35. That is type 2 error. What is it? That's part's done. Describe a consequence. So what's the consequence of this? So you would report back, if you work for the recreation department, you would report back that you believe that this proportion is 0.35. So what is the consequence of that report you would give? Let's see. So what is it saying here? The council is facing budget constraints and is skeptical of the report. The council will fund more physical fitness programs only if the recreation department can provide convincing evidence that the report is true. So the report said, a recent report stated less than 35% of adults in a certain city will be able to pass the physical fitness test. So here's their condition. If the report is true, then they will fund this physical fitness program. So if you come back to them and you report that we found the report to be true, we do believe that there's less than 35%, the proportion is less than 35%, then they're going to go out and write some checks and support and fund this program. However, what's your conclusion? Your conclusion is that this is actually not the case. You are going to report back that 35% of these adults in the city, only 35%, no less, can support or can do or pass this physical fitness test. Although the true reality unknown to you is that less than 35% actually can. What is the consequence of this? The consequence is the city, the rec department, does not fund this physical fitness program, fund this program when it actually should. That is the consequence of making that error. And that error is just random chance. That is something that we cannot, that's out of our control. It's just based on the data we have and the sample the data from our sample that we took. And even if we did everything right, there's a chance that we make this type of error. So sometimes when people are actually doing this in practice, they need to really weigh what are these errors? Like what are the errors I am possible to make in doing this hypothesis, doing this test? And if one of these errors, if they don't feel good about about one of these errors, or maybe the error has a very significant consequence, they may not carry out this test, and maybe they'll find something else to do because it's really high risk. Think medical, for example, testing drugs and things like that. And if there's a chance that they are going to make a conclusion, for example, that like if their null hypothesis is that these two drugs are equally helpful and their alternative is that one is better than the other, if they go out and they find, they do this study and they have, let's say, quote unquote, they have a sample that comes back and a test that says, oh, you know what, these drugs are equivalent. They're really not, one's not better than the other one. Okay, that's what you report back. But what if that is actually not true and you just sort of had maybe just a randomly bad result? Then there's a problem, right? Because if one drug is better, then that drug should be out there helping people heal or whatever it might be, or get better from whatever they're suffering from. So that would be a situation where you would have to weigh the consequences of that error in your hypothesis test. So these are the essentials of type 1, type 2 error. And the last little bit that I'm just going to mention is, I talked about the probability of type 2 error here. Type 1 error, its probability of type 1 error is actually the significance level. And if you think about it, when you look at this one, the one that we did over here, what was the probability of type 1 error in our data? The probability type 1 error in this context, when in our little simulation, we only had one wrong conclusion where we rejected the null hypothesis when it was actually true. If you remember, our machine had 50% orange. That only happened 1 out of 10 times. This probability of type 1 error is 0.1. This significance level is literally the probability that you reject the null hypothesis when it is true. And that's why when we have p-values that are less than 0.05, this statistic falls in the rejection region, the critical region, and it gives you a p-value that's less than that. It would fall if here's 0.05, if this area over here is 0.05, this p hat, 20 out of 30, mark it in green, would have fallen somewhere over here. This would have been your 20 out of 30. And its p-value would have been calculated over here to 0.34. And so really it's just this little region right here. I'm going to highlight in yellow. It's just this region right here that rejects the null hypothesis. Anything else, anything that falls over here, any sample proportion that falls here or over here, it's not going to reject the null hypothesis. because this p-value is going to be too high. So really, this number, this is the probability of type 1 errors. So I guess the last thing I would add to this before I end the video, and I hope this helps. I think doing this little activity does make a difference. You might have to split this up over a couple days or a couple sittings, but probability of type 1 error, that's the probability that you reject the null hypothesis given or if, remember that's how we read that, conditional probability, reject the null hypothesis if the null hypothesis is true, just like we had here when this was 0.05 or 0.5 and our hypothesis was 0.5, we guessed correctly. That is equal to your significance level alpha, and in this context it's equal to 0.05. So I hope this video is helpful. I think this is a really good example of what this looks like. So take care. Have a nice